My name is Jonas Karlsson. I work here at Google. And I'm very happy to introduce my professor, Risch here from Sweden. He has somehow somewhat a Silicon Valley history. He used to be at HP Labs in the database lab there. Did very interesting work on kind of object relational database system and main memory database systems. And he's also been part of a number of startups in AI and knowledge management. And now he's professor in Uppsala in Sweden, database lab. Formerly he was in Linköping. And he learned me a lot about databases, especially database implementations. So if you're really interested in that, you can have a really good discussions about that afterwards, or whatever. This is a talk which is recorded for open audience of Google videos, so please be careful with what questions you ask, so don't ask anything confidential. We will have an ability to ask those questions after the talk is finished, if you have anything, so just be careful about what you mention. And with that, I let Ture have the floor here.
Okay, thank you very much for the introduction. Yes, I'm going to talk about a project, actually two projects that we have been working on recently. And the title is Customizable Scalable Compute-Intensive Stream Queries. This talk is mainly based on the first publication here with me and Milena Ivanova. It was a VLDB conference in Trondheim, which was sponsored by Google, I think. And that's the main part. Now, Milena has moved over to Holland, to CWI. And we are continuing, it's a follow-up project with Erik Seidler, and I will mention a little bit about what we are doing there, but this is more ongoing work, the second one. Okay, so this has been recognized a lot recently that we have new, very data-intensive applications. And where data is not stored on disk as they are in regular relation databases, but they come in large streams. And what we have been particularly interested in, like satellite data or space data. Scientific data, you have things like different kind of measurement devices that manipulate this data coming down. Patient monitoring, stock data, process industry, and traffic control are other examples. But we are mostly interested in the scientific part, so it's the first part here. And the interesting thing with these new kind of applications is that data come in streams rather than being stored on disk. And these streams can be big. So then there's been a lot of interest in doing something called a data stream management system. You know, we talk about database management system. A data stream management system is something which is actually rather similar to a database management system, but it is also different. And this picture is actually a modification of the major textbook on databases, in fact, but it's now, instead of the database management architecture, it is data stream management architecture. So on the top, it is the same. You know, you have users and programmers, and they pose queries to the system. As not SQL, maybe something else. And then you have this big piece of system software called the Data Stream Management System, or the DSMS. And it has some software to process queries. And if it had been a database management system, there would have been a lot of software to process disk. But here there is instead software to access streams. And exactly as a database management system, you input some metadata, a schema. And the input, basically what it does, it accesses streams, and the result of a query in the relation database is a table. Here the result of a query is a stream. So stream in, stream out. So it's rather similar, but actually different. Now we want to see what kind of applications we have been looking at. And I've been, you know, in Sweden for a while, and I've been looking for real challenging applications. And really, we got it in Uppsala, where they have a lot of physicists. So this is what they're doing in Holland. They are building the first in the world all software radio telescope, no moving parts. Instead of having these big steel things, you know, what they are doing is they're putting out a lot of transmitters in this pattern here. Every dot here is a transmitter station. And there's some software and hardware over there, and it receives data in all directions from space, collects it into fast Ethernet cables, and it all collected into a central processing unit in Groningen in northern Holland. So now the stream rate here is pretty enormous. It is 20 terabits per second altogether, and they really needed a good computer. So they bought one of those blue jeans, IBM blue jeans, and that's what we're running on actually these days. And actually it is not even a standard blue jean, it is a specially configured IBM blue jean for handling large stream volume, because the blue jean is really for number crunching only, and here we want to deal with streams. And what we have been working on here now, and now you can actually see what the scientists are doing, the astronomers are doing. They're looking for phenomena, things happening up there. And what they basically are doing is that they are putting filters on the streams. I want to see when there is this kind of solar storm or something. Yeah? And so this can be seen as a stream query. But the way you express the queries is rather different from SQL, because you have these rather advanced filter operations. And the astronomers know how to do that. It has to be possible to plug them in. And it is also very challenging because there are many computers involved, there are several clusters involved, and it's an enormous amount of data. And it's much more fun than just business data from our point of view. Yeah? And here's the reason we came into it, because there is an associate project called the Lewis Outrigger in Sweden. So the physicists in Uppsala, they have been setting up, they're very specializing in antennas. So they have special kind of, these are software, all software antennas where you can program the direction where they are sensitive. By the way, this telescope, so you program the lens in software, and then you can actually program the direction. Because if you want to look in a certain direction, there's going to be a difference in time. There was going to be interference between. So you can program direction. So you can actually say, I want to look in that direction, and then you can look more carefully there. And similarly, in fact, these antennas you can program in different directions. They're all software directed. So anyway, so this is connected to it is in collaboration with the LUFA project. And they actually have set up this antenna. This is a real photo, in fact. And this data is being fed out into the internet as a UDP stream. And we are actually been querying this UDP stream. And there's some hardware in there to do that. Okay, so now the first thing to do is to look at requirements. Well, first, the real challenge here is the scalability. Because the data volume now suddenly is something we have never seen before in the database world. In fact, the insert rate is pretty high. In a relation database, it's for business. Yeah, you want to insert quite a lot of records, and you want to access them pretty fast. But it is not at all this rate we're talking about. The data volume is much bigger. And one effect of this is now you can talk about, even in stream databases, why don't we just store the stream on disk? But in this case, no, it is too much. Data has to be reduced before it can be stored on disk. And another thing is you cannot, well, this is true for all stream database management systems, that you cannot query, do join in the regular way. Instead, you have to look at pieces of the stream at a time. That is what's called moving windows. So you always look at windows that slice over the streams. And that's where you make the queries. And that's how it works. And then on these streams, one apply different kind of filterings. And the filterings are, well, there are regular filterings like you have in relation databases, but there are also special kind of filterings that are made by the astronomers, to do the signal processing of different kinds, signal reduction algorithms. And you also do combine. Very important here is actually join, because what I said, when you aim the telescope, you look at difference in time of the signal, of the stream, from different directions. And also, both filtering, reduction, and combination has to use user-defined functions. It is not enough to just have a set language, like in SQL. And it has to be scalable with respect to data volume, but the problem is that these algorithms they have for combination and filtering, they're rather expensive. So it has to scale when you have expensive computations too. If you have a relational database, the computations you're doing are very small. It is comparison of different kinds. And indexing is the main thing. But here we also have rather expensive computations being done in real time on the streams arriving. So this is requirements. So what we did then, and this is the first, this is the main part of the talk, and that's the BLDB paper, something called the Grid Stream Data Manager. It basically is a stream data management system that is specialized for very high volume scientific data. And as other stream database management systems, you define continuous queries over them, filter conditions. And you allow user-defined functions, very important, because you have to be able to plug in your own C code. Now, to get the performance, this is a parallel or distributed system. It is not running on one node, it is running on many nodes, arbitrary number of nodes. And they can communicate with each other, and the system can dynamically start new nodes or even kill nodes. It's completely dynamic, so it's a dynamic architecture. And what the paper was mainly about was how do you define the computation in such a distributed and parallel environment. And what we have is a way called data flow distribution templates. It's a way of, for a given algorithm, you know, foreign functions have been used in databases for a long time. So you can easily define your own code in C and then use it in queries. But the problem is if you want to parallelize it, you also want to tell the system how to parallelize an algorithm. And this depends very often on the algorithm. And I will talk a little bit more about that. So there has to be a way to customize the parallelization as well. And that's what data flow distribution templates are about. And of course, in order to get the performance we need here, the engine itself has to run in main memory. There is not time to save on disk. Yeah? So here's a scenario how you use the system. So you are a scientist to the right here. And the scientist talks to some kind of a client program and will get the result back of the query normally as a visualization program. You don't want to get just numbers back. You have some kind of a graphics for that. And then we have a coordinator, the GSDM coordinator, and then we have access to some cluster. It can be more than one, in fact. But right now it's only one. One cluster, and here is a radio signal. Yeah? And this is very high volume. Yeah? So what happens then is that the client specifies a continuous query and sends it to the coordinator. And I'm coming to the details how this is done later. But basically you use these templates to define it. The coordinator, when you say compile, the coordinator generates a logical distribution graph. This is a data flow distribution graph describing how to do the computation. And the system knows then for a given query how to parallelize it. So here it is using this template to generate this logical graph. Now you want to run this. You say run. And the first thing that happens is run is that the coordinator download the code to execute that graph into the working node here. It starts 4 working nodes in this case. It downloads different pieces to the different nodes. But it starts them first and then it downloads. Now it downloaded. Yeah? And here you can see, well, you can get an idea what is happening. It's doing partitioning here. We have 2 partitions. This is partition 0, partition 1. It's a partition. And then we do parallel computation here. In this case, it's fast Fourier transform. It's not the normal one, it's FFT3 because of this antenna which has 3 dimensions. And then what you want to do is to merge it together. And this is how you get speed out of FFT, because FFT, if you parallelize it, you can get good speed out of it. Okay, so we install it, but you can do that in different ways. And here it runs. And then it starts to flow. So data flows through here and you get visualization in the other end. But everything is completely dynamic. Okay, and this is how a node looks, by the way. So a node has an engine, the query executor, and it runs a loop to receive the logical windows. And it schedules then, there are some incoming, there's an interface called the stream consumers. And here I have an interface to what they call a beam. Beam is the astronomer's word for radio signal for me. Yeah, you look at the beam. Yeah. So there are 2 beams coming in, but it can be another GSDM node. And the result can be an application. You know, if you looked on the previous page here. This one. No. So, that one. You see application here. Or it can be another GSDM node. And the interface.
Is that beaming the merged data from the separate antennas, or is that each a separate antenna?
Good question. Actually, if you look at how it is really done in practice, well, in the Swedish project it is 1 antenna, yes. In the Dutch, I think they have a station where they first do some combination before they sell it to the central computer. But this is, I mean, the problem here is also that you can configure these things very differently. And this is part of the optimization problem. Where do you want to run what, and where do you want to collect what? All I wanted to show with this picture is that we have something like an engine that you can have interfaces to input stream, or interfaces to output streams, and you can combine them in any. And then the optimization problem is how many of these are you supposed to start, where and when? Yeah. And by the way, plugins is very important because you have to be able to plug in your same code, your application C code here. Okay. So now the data flow distribution templates is basically high-level primitives that we provide, where you can define your own execution strategies. You can, for example, define, as I will show, how to parallelize FFT in 2 different ways. And now it turns out the following, which is very interesting. A data flow distribution template can be independent on what you're going to compute. And for us, that's something which is built into the system. But we can look at it like a customization too, you know, the generic one. And we have defined one which is called window distribute. And this is actually what people are doing with distributed databases. We do round robin, you know. First window there, then that, then that, then that. Yeah? So by round robin, it distributes the window, and that's FFT parallel in each window. Well, the problem with that is that the window is not smaller. So the FFT will still be slow. So it turns out that if you have something advanced, like even such a simple thing as FFT that everybody knows, you want to like to do the partitioning customized. And so window split allow you to do your own customization here. And now it depends. What you want to do is to split the big window into smaller, and this depends on the algorithm you're running. And for FFT, there's a special way of doing that. For other algorithms, there's a different way. So that's window split. And then the interesting thing is that you combine it all into something called the PCC, partition compute combine. It is very, very common that what you want to do is first do a partition, then a parallel computation, and then a combination, as I showed. And it turns out to be this one is defined in terms of the others. And this is what you normally use. So we provide PCC, but actually PCC can then choose. You specify what variant of PCC you have. I come to that. So stream query function is where the computation is being done. Here I just have on a very high level, in fact, definition of such a stream query function. Stream query function basically takes the content of one or several logical windows, combine them, and produces a stream of logical windows. And what we want to do in this case is we take the current window of one input stream, in fact, and then we apply FFT. Here you see X, Y, and Z. Remember, it was three-dimensional antenna, so we want to do it in X, Y, and Z coordinates. So we pick up that component of the window, we put a timestamp on it, and we compute a new radio window. But the main computation being done here is a single FFT. Now it's a regular FFT suddenly. It's three regular FFTs in our case. Yeah? So we have that's why I call FFT3. Very simple. So this is a very small program, in fact. Of course, somebody has to implement FFT, but that's well known. Okay, so the idea here is to define customizable distribution templates. And the continuous queries are defined as compositions of stream query functions. And what the system does is to assign logical sides, patterns like this. Yeah? And basically what a DFDT is, it's a constructor. It is a constructor of this structure here, data structure. We want to say we want to do something here, and then this connects to that. So you basically just construct this graph. So it's actually a very simple program. And PCC is that it's it's a parameterized constructor. Constructors take parameters, and it can in general construct these kind of patterns. You know? And you want to scale here the number of parallel computations. Of course, then you pay a price here and a price here. And this you also would like to parameterize. If you wonder what this 256 is, that's the size of the window. If you do this round-robin thing, it turns out what you're doing is to send the same window size. So if it's 256 in, it's going to be 256 on each FFT, and it will be size 256 out. Yeah? Okay, and this is how you use it. So it was also on that other slide. You know. First you say, I want to do PCC, I want to use 4 nodes. I want to do this stream distribute, and it takes as parameter round-robin partitioning. Yeah? That's a function. Yeah? All our functions. You take this distribute function, it takes our partition as a parameter, and then we want to apply in the middle FFT3, and then at the end we will do S-merge. And S-merge actually takes a little timeout parameter, 0.1. See, the parameter can be functions or it can be numbers. Yeah? And then we define the stream, and that's rather straightforward. We want to read this as an input stream. It's called radio. It's some kind of radio signal. It's on that port or host address, and it's a UDP. Yeah. Because that's what they deliver to the Lewis project. And then there is on 1, 2, 3, 5 we have the visualize. So that basically is it is listening according to some kind of visualization protocol, which we implemented then. Yeah? And then you compile it. Compile this this query with this input and that output, and you want to run it on this cluster, which is our cluster computer. It's a Linux cluster we have in Uppsala. Huh? And then run it. That's it.
Question?
Yep.
Can you dynamically determine how many nodes you use, or do you have to statically set that for? So you said it sets 4 nodes there. Do you have
in the plain PCC, you do that. At the end, I will mention that we have done yet another one, which which actually dynamically does it. But typically this is also determined by how many resources you have. This is the thing, you know. At least that's the way it works in Uppsala, is we have to reserve a certain amount of nodes. So we have to know, in any case, how much resources we have. So in any case, you have to set an upper limit on how many resources you have.
Will that change during the execution period, especially if they're long queries?
Not on our, well, that could happen, but we don't support that, and we don't have that in Uppsala either. We have to pre-allocate all the resources in Uppsala for the moment.
Please?
Yeah.
Repeat the questions. Repeat the questions.
The question is, can it dynamically change the number of nodes during runtime? Not in our current implementation. And furthermore, the way we use the cluster in Uppsala, we have to use the cluster, we have to pre-reserve how many nodes we can use. We have a certain allocation of nodes. So, and typically what you would, in any case, to have a maximum number of clusters.
From my understanding, I have to copy the input stream into like the 4 nodes that you'll be using on the cluster for.
Copy. Yeah, it streams.
Yeah, but I mean,
Copy, did you say copy?
Like, you have to transmit them somehow to the 4 nodes.
You using TCP,
So
yes.
so you'll have like 4 copies on 4 machines on this cluster.
Of the window.
Of the window.
Of the window.
Not of the whole stream.
No, absolutely not. Absolutely not. That's why there is a loop, you know, under here. Okay. There are some requirements now if we go to partitioning, like for FFT. First of all, if you're going to do a parallel implementation of fast Fourier transform, it better return the same result, or at least approximately the same result. Yeah? And furthermore, in difference to relational databases, another important thing with streams is we have an order. They come in an order, and we don't want it to reverse order of logical windows necessarily. And for it to be good in any case, you know, it has to do some kind of load balancing. You know, if one node is doing all the work, we haven't gained anything, obviously. And so examples, and window distribute and window split have this property. Okay, so let's do the first simple one that everybody knows about. Run, robin, window distribute. This is a generic method. It can be applied. It's used in many distributed databases, very, very standard. And it is SQF-independent, independent on what you're going to do. And the only thing we're doing is to distribute the logical windows to different nodes depending on, in a round-robin fashion. And then the computation is being done in parallel on those, and then it's collected. And basically, we have a generic function sdistribute, and here is a partitioning function, and it's computation, and then the merge and the timeout. So basically, it consists of three parts: a distribution phase, a computation phase, and a merge phase. And this call will generate this graph. And once again, you know, our part is a user-defined function on the next slide that says this is 0 out of 2, 1 out of 2. So every second goes there, every second goes there. The size of the window is going to be the same all through. This is how you define it, trivial. It basically says it's a sliding window. That's very important too, by the way. And you're sliding with a certain step. So you take a certain amount of data and you get an array back. And then we select the ends, the P and O number out of that array. Sliding window basically collects the incoming stream elements into arrays of a given size and then jumps forward. But that's it, you know. Select P and O out of P tut, yeah, in the sliding. Of course, sliding window is built in. Okay, so window split is interesting now. It is dependent because now we want to customize this. We want to do this, but we want to do it so we can use it for the FFT. Now FFT you can use window distribute, but it will not speed up as much as if you can make the window smaller. And it turns out to be something called the FFT radix algorithm that allows you to do this. And now we do the partition according to FFT radix. And basically it is the same, but the only difference is PCC, but we use something called operator split and operator join. And here the partitioning function is called FF3 partitioning, and this one is called FF3 combine. And these are much more complex than just round robin, because round robin just selected. Yeah? So here basically what happens then, it will do FF3 partitioning 0 out of 2, 1 out of 2, and then do FFT3 in same FFT3, and then the combine. And here it's using the combine function as an argument. And an interesting thing here now, if the incoming size of the window is 256, here there will only be size 128. And since you know the complexity of FFT is n log n, this is going to be faster. Yeah? But the problem is that it's not at all application independent anymore. And here is how FFT3 part actually is implemented or looks. Basically, it takes a window and it picks up the X, Y, and Z coordinate, and then it applies a user-defined computation here to pick up, actually picks up elements in a certain order. And then it forms a new radio window. So this is only on the higher level how it is done. The real work is done by this FFT3 part on one. But as I said, it's XYZ, so it's three times FFT. But you get the idea, you know, you define your own partitioning function. And the interesting thing now is that to really make this powerful is, wherever you put a function, you can put a template. So suppose you want to make this thing. This is actually PCC, S-distribute with round-robin partitioning, and we are calling PCC in the middle, and it gets this argument. We are doing a 2 here, distribute partition, so it's twice recursively doing distribution in 2. So now you can see what you can do here. You can create enormous patterns here, very easily, but since you can call it recursively. Now, if this is faster or not is a different story, but there are cases where this is faster. Now, it turns out in our case here, it wasn't that necessarily, but could be. And the nice thing then, we get rather small windows in the middle here. What you can gain here is because one speed up the distribution phase compared to the other one, if there's a high cost on distribution. And the same for merge. You get more balanced. On the other hand, you use more nodes. But you get the point, you know. By having this recursive, we can generate extremely complicated patterns. Compare this to relational databases where it's more chaotic, you know. You try all kinds of orders. Here we have a certain pattern generator. And it's only constructors. Yeah? Let's go on. So we did some experimental results, and they are, we did window split, window distribute. Actually, central, by the way, it's another template. It's really, the distribution is null, and the join is null. Yeah. So they are all expressed as templates. So centrally execution we get as a very trivial special case. And we did some scalability. We actually, on the measure in the paper, was only maximum throughput. But we have also, we can change, you know, it depends on the metrics. If you want to do delay, we can do that as well, which has been done, in fact. And what the astronomers want to do, they don't want to use only 256 size. Because remember what they do, when they have a raw signal, and then they do Fourier transform, they want a frequency spectrum. And then you want to tune in the frequencies you're going to look at. And the bigger window you have, the more you can tune. So the bigger window you have, the more information you have retained, you lose less information. So what we would like to do is to scale the window size. Yeah? And we scale it quite a lot to 16K there. And then this is heavy duty. And we measure the impact of communication and computation. And another thing is the speed of the algorithm does matter. And we did this rather simple. We took FFT and we introduced some artificial delays in it. So it became slower, to see what happens when it gets slower. Yeah? And this is the first. Here it's just 2, you know, split what I had on the picture. And you can see central is slower, apparently. And window distribute is slower than window split. You don't see, well, it depends on actually how much. We didn't slow down the algorithm enough eventually. If you had slowed it down more, the difference between these two would have been great. Okay, so now we did degree 4 instead. We split it in 4. And here we also tested the 3, the recursive one. And it is still a slow computation. And it turns out that if you look at the array, when you have small windows, the window split wins. And you know, this is exactly what they do in distributed databases. You have small records. Window split is a good, which is a standard round robin. It's standard distributed database splitting. It's good. But once you start to get into complex computation, once the computation starts to matter, then the window split wins. Window distribute wins for small records. Window split for big, yeah, big windows. And one can also see it here, you know, that window distribute is slower here. On the other hand, the problem is that the partitioning combined algorithms are more complex in this case. yeah, because it was very simple partitioning and very simple combination. So the thing is, the more work you have to do, the better it will be to use window split. Okay, we did also with a fast, highly optimized implementation of FFT3. And here it starts to show that actually the tree is best. On the other hand, then it's not so heavy computations as before. And you also see that for small, well, it is, if you think of it, it's the same picture, it is just shifted. And we can just deal with much bigger windows now. That's the main difference. So for small windows, you still have the distribute is better, but for big windows, and the bigger windows, the better it is to do split. Yeah? So apparently there is a trade-off between one or the other. And one can also see it here on these graphs that the bigger the size, the more overhead you have on the FFT. And this is because of the complexity of the FFT. And then the split algorithm, the split partitioning starts to pay off. Okay, is that clear? Here we have plotted it where you see how much is the speed up compared to central case. And you see there's a window of opportunity. There is a window of opportunity for the window distribute here, but when it goes larger, it is bigger. By the way, you see this point over here, that's the tree distribution. The problem with the tree distribution is you use much more nodes. And the thing is, you would like to do the split strategy when there are some limitation on how many nodes you have, if you have some computation limitation. And so you have a trade-off here, you know. If you are doing too complex or too big patterns, you're using too many nodes. And then it might not pay off. Depends on how many nodes you have. Yeah. Now, if you want to look at related work to this, first of all, there's a whole bunch of work done on data stream management systems recently. And Aurora is probably the most famous one. Well, I shouldn't say that. It's one of the most famous ones. It's Stonebreaker and company on the East Coast. And there's a stream project at Stanford on the West Coast. And there's a Gigascope at AT&T, and there's a Telegraph CQ on the West Coast by Stonebreaker's former guy. And basically, the first generation data stream management systems, they were all central. It was like a central database, but they deal with streams. So the main difference here is to have a distribution and that we can do advanced numerical computations. We are not just dealing with simple things. And you can have large stream windows. Interesting is, recently people have been starting to look at parallel stream database systems. And there's a Flux at Berkeley on the East Coast, on the West Coast. And Borealis is the successor of Aurora on the East Coast. And basically what I've mostly been looking at is load balancing and fault tolerance. And the main difference is that we are looking at these expensive computations and how to use customized distribution templates. And then, of course, in the distributed database field, they have been dealing with partitioning for a very long time. And they basically have only generic ways of doing it. And they always assume small windows or small data records, round robin hash and range. In our case, we provide that too, you know, that's just another customization. Conclusion. So we have been looking at how to do continuous queries where you have expensive user-defined functions. And it's not enough to just implement them in C or something. You also have to specify how to distribute distribution patterns. And this is done through this language or constructor, set of constructor templates we have, where you construct the distribution templates. PCC is one generic such one, which is a very common pattern when you first distribute and then combine. And it is yet another one only. And then then you use that in combination with either window split, which you can use for any function you want to compute, or we have done a special one. No, window split is computation dependent, and we have implemented it for FFT radix. We measured on that. Window distribute is a generic one that will be in a distributed database as well. And this is in application independent. The split is dependent. The split is good when you have expensive functions like the FFT, which is slower when you have big windows, whereas a distribute is pretty good for small operations, it turns out. And where actually the size of the window doesn't influence the speed of the algorithm. That's about that. So you mentioned something else. Here we have, now this has also been done, in fact. You can define another template called opt. And here, opt, you do this I want to optimize PCC with respect to FFT3. And what does this do? Well, it looks up what are the templates defined for FFT3, and then it varies the parameters. And it runs a profiling program. It stores the profiling data in a database, in the same database, in the coordinator, and then it chooses the cheapest one. And okay, you know, this takes 10 minutes. But then you run it. Yeah. Why not? So that's how so you can do specialized optimizers this way. And this is not complex. It's about 200 lines of code or something. So I want to talk a little bit about the continuation of this, a very exciting thing called SISQ, Supercomputer Stream Query Processor. And as I said earlier, in the LUFAR project, this is mainly together with LUFAR. The other one was primarily in collaboration with Lewis, but these projects are together. And they have then this IBM Blue Gene, which is a very different kind of computer than we have been used to before. Not very much, but somewhat different. And we want to do the same thing, you know. We want to do scalable search and processing very high volume data. And this is scientific data, certainly scientific data, astronomers. So it's the same application area. This is how it looks. So it is really standing there and how it looks in Groningen, in fact. What is special with this new computer is that first of all, there are 12,000 processors in Holland. But Lawrence Livermore, you know, they have 128,000 in Lawrence Livermore. That's the biggest one. But this is the biggest in Europe. So 12,000 processors. Now, one problem with so many processors is energy. It generates a lot of energy. So what they have done is to deliberately make them slower. It's only 740 or something megahertz. So they are rather slow. But that also means that every processor only uses 10 watts. You have to compare that to a PC. Just 100 watts. So they're rather slow. However, it turns out that it's a fantastic communication between them. It's a gigabit network between them. So it's very, very fast communication between these nodes. And you have about half a gigabyte of main memory on each node currently. But that can be increased. Yeah? Another thing to make this lightweight, this system, they actually do not have full Unix at all on this. They have a subset of Unix, but it is really a subset, which is very nice. So if you don't do certain things, you can run your standard Unix program, yes. And so, but you cannot use threads. No. There are different kinds of nodes, in fact. Some nodes are specializing in communication with other nodes, and some nodes are specializing in communication with the outside world. And some processors are doing computation. So you can do different things on different nodes. And there are different kinds of communication channels. So you can choose different ways of communicating between these. So there's lots of tools here. You know, there's lots of hammers, but you have to know how to use them. And the way some people do this is they do an assembly program, you know, to make a very, very fast implementation on a Blue Gene or whatever they want to do, like some kind of signal processing for LOFAR. That has been done, you know. And also it is said by IBM, I heard that said, this is not designed for mainstream DBMSs because it's much better when you have asynchronous processing. And it turns out that this is what we have, stream processing asynchronous. I should say something more. The particular Blue Gene they have in Holland is specially configured for stream management. What that means is they have a lot of incoming connectors, yeah? What you call it, gateways. But routers, yeah. So there are a lot of incoming cables basically into the computer, and also out. Much more than in Livermore. What I heard is if you try to do the same with 120,000 processors they have in Livermore, it will be very high cost. You know, so there's a trade-off here how many nodes you can have, depending on how many input connection you want to have. So And this is how it really works, which even makes it even more interesting. You see on the top there, we have the input streams from the antennas now distributed over Holland. They go through this fast Ethernet into a back-end cluster. And the back-end cluster is just a regular Linux cluster, regular IBM Linux cluster. And then there is a fast connection between the back-end cluster and the blue gene. And in the blue gene, this data reduction is being done. And then reduced data goes to the front cluster. And then the user will see it. And now in our case, we are basically submitting stream queries. And it is going to start up nodes all the way, not in the input stream, but from the back end on the blue gene and on the front cluster, all three of them. And these are going to communicate with each other. Yeah? And both the front and the back end are Linux, regular Linux. And here you can see what are the components. What we call preparators is what this pre-filtering being done in the back end Linux. And then we start a bunch of SP here, stream processor, or that's the same as working nodes in GSDM. And there is a coordinator, a compute node coordinator, which starts this. And and this is stream, the big arrow. And there is a query master which collects the stream and sends them over to the front stream processor and then over to the client. And here typically you do visualization, here you do data reduction, here you also do some data reduction. One particular problem with Blue Gene is that you have to start exactly the same software on all nodes. It's the same, these are identical executables. But this fits well with our model, because what we do is we start the same executable and then we install code that is being interpreted on each node. So even though they have been thinking of it like running the same software on each node, on every node, we are able to run almost anything. By the way, they're using MPI here, native MPI for communication, which is pretty interesting actually. And there are lots of hooks here. So research issue here are, you have to include hardware specification in optimization, like how to use the communication in a good way, how to use the different node specializations in a different way. You do different thing on the back end, in the blue gene, and in the front end, for sure. And then you have these limitations on the OS and what are the opportunities. There are no threads, but instead of having many threads, one can use many processors instead. Yeah, so it's very cheap to have more processors instead. And you have lots of main memory. And you want to optimize the streams across several different clusters, and you want to do customization exactly as we did in GSDM here as well, actually. So that's it. Yeah.
How do the system deal with the crashes, nodes and
Crash?
Yeah.
That is not an issue here. You restart it. Yeah. What? How we deal with crashes? Crash. No, we are not currently dealing with crashes. This has been, of course, studied in the data stream management system area, that they talk about how to recover streams. And one way to do that, according to the literature, is that you have some backup nodes for that. You can do that. You can mask crashes. But that would mean that you would have to introduce that.
So do you do any stacking of like window split and window distribute? Because split's good for big data sets, right?
Yeah.
So you can split down the smaller ones and then distribute. Is that what you do?
It is.
Repeat the question, please.
Yeah. Do we do any stacking?
Yeah, like do a level of split, and then distribute on the window.
I think what you mean. Maybe what you mean is this. Is this what you mean? That you can stack them on each other.
Right.
Yeah.
So,
but this is a template. I mean, this is by just using the template recursively, we can do a staged split. Is that what you meant?
Right. I'm saying, did you do any tests where you did a split and then a distribute? First do a split and then do a distribute.
Aha. Well, that you can say. Well, what is the difference between split and distribute? Maybe that's the problem. In this case, it's going to do a split here. Well, it is split. What is the difference? I don't understand the question, I think. What is the difference between split and distribute?
Right, because split's doing a radix, FFT, right?
Yeah.
And distribute's just going to do regular FFT, but on each window, it's doing the round robin push, and then it does regular FFT.
Exactly. So this is the overall distribution algorithm. And it takes as parameter a partitioning function. And this one has the knowledge how to do the partitioning and when to call the customized partitioning function. Did I understand?
There's this one.
I mean, I know you have something called map reviews here. So, and of course, from my point of view, that is another kind of distribution pattern, actually. Yeah.
All right. Any more questions? So thank you very much for attending, and you can watch it again on Google Video. Thanks, Stuart.